Okay, let's unpack this. We rely on AI for so much today, right?
Absolutely. Image recognition, data analysis. It's everywhere.
But what happens when the AI runs into something weird, something it really hasn't seen before, outside its training data?
Uh-huh.
This isn't just theoretical. It's a huge, real-world problem for using AI safely.
It really is. Because, AI models learn patterns. They get incredibly good at stuff within the data they've seen.
Right.
But the real world throws curveballs, something different. And the model, well, it often doesn't have a way to say, hey, I'm not sure here. It just gives an answer.
Even if it's confidently wrong.
Exactly. Confidently wrong is the scary part.
So our mission here in this deep dive is to explore how we build systems around these models to catch when the input data might be a mismatch.
These out-of-distribution samples, or black swans, as the sources call them.
Yeah, like giving the AI a way to kind of raise a flag and say, whoa, hold on, I'm not sure about this one. And we're guided entirely by your stack of sources here, which map out different strategies.
And it's crucial, right? This isn't just about error checking. It's fundamental for building trust in AI, especially for things like healthcare or, autonomous driving.
Definitely. Okay, so before we get into the detection strategies, let's quickly touch on why this is so tough. Your sources mention some basic limits of AI learning. First up, generalization mismatch.
Right. So AI learns from, well, a finite set of examples. It gets good at local patterns in that data,
Okay.
but the real world, it's infinitely complex, way more diverse than any training set. That's where you get these data distribution
Like
shifts.
the example in the source.
Yeah, the Arctic fox one, great example. If the AI only ever saw pictures of white Arctic foxes,
Uh-huh.
it might totally fail when it sees one that's molting and has gray patches.
Even though it's still an Arctic fox.
Exactly. The visuals are just outside what it learned. It's out of distribution for that model.
So it saw a fox, but not this fox looking like this.
Okay.
Then there's pattern mismatch.
Yeah, this is related. AI leans heavily on the fixed patterns it learned. But the world changes. New things pop up. If something new doesn't fit the known patterns, the AI might, well, misapply an old pattern or just stall.
Like the other example, dogs and apples.
Perfect one.
Yeah.
AI trained only on dogs and apples sees a fox
Oh.
and maybe calls it a dog. Because it doesn't have a fox pattern, it just jams the new thing into the closest box it knows.
Trying to fit a square peg in a round hole because that's all it has.
Pretty much.
And that leads to something really concerning, error blindness.
This is a big one for reliability. Current AI just lacks, well, metacognition. It can't really judge its own judgments.
It can't think about its thinking.
Exactly. It works on statistics, probabilities from the training data. It gives you an answer, maybe even a high confidence score.
Yeah, like 99% certain.
Right. But it doesn't know if that answer is actually correct in the real world. It can't reflect. It doesn't have that human sense of, maybe I got that wrong.
The confidence score feels like certainty, but it's just math based on the past.
Precisely. And tied to that is what the sources call solution deafness.
Okay.
Once it's trained, the model structure is pretty rigid. Like the source says, hardened cement.
Ah.
It's not built to just take feedback easily. You can tell it, hey, that gray fox wasn't a dog, but it can't just update itself on the fly.
So you can't correct it easily.
Not really. Big changes usually mean going back and retraining it with new data, which is a whole process.
Okay, wow. So models trained on limited data, struggle with new patterns, don't know when they're wrong, and they're hard to update. That's quite a set of challenges.
It definitely sets the stage for why detection is needed.
So how do the sources suggest we detect when an AI might be making these kinds of errors because of the input? Let's dive into the strategies. Strategy 1, Model A. Sounds like the starting point.
Yeah, Model A is the simplest idea. You take a single AI model. The source mentions EfficientNet, which is a common type of CNN.
CNN, so it's good at images, looking at local details.
Right, exactly. It looks at parts of an image and builds up. So you take that model and you run the same input through it multiple times.
How many times?
The source specifically says 3 times.
Okay. Run the image through the same EfficientNet 3 times. And the rule for detection is?
If the model gives you the same answer 2 or more times out of 3, you assume the data's probably okay. It's in the model's comfort zone. But if it gives you a different result all 3 times,
Then you flag it.
then you flag it as a potential data mismatch. Yeah.
Okay, so you're looking for the stability of the prediction from that one model.
Exactly. You're leveraging a bit of the model's internal workings, things like dropout, where parts are randomly ignored during prediction, or other little random elements.
The randomness that usually helps it generalize.
Right. But here, you use it as a test. If the same input gives 3 different outputs when you run it 3 times, it suggests the input is hitting a blurry spot for the model.
An area where it's not confident.
Yeah, where that internal randomness causes the output to jump around because it doesn't see a clear, strong pattern it recognizes.
Okay, I get it. It's unstable because the model's uncertain.
Mm-hmm.
Pros seem obvious. Simple, low cost.
Super simple, cheap to run.
But the cons.
Pretty significant, actually. The detection ability is rated low because you're totally reliant on one model's view.
No, right. It biases its blind spots.
Exactly. That model could be consistently wrong. Maybe it always calls the gray fox a dog, but it would still look stable by this method.
So consistency isn't correctness here.
Not at all. Especially if the data is consistently outside what it was trained on, but in a way that fools this specific model.
Okay, so it misses the confidently wrong cases if they're consistent.
Yeah. And it also fails if the OD data is just similar enough to the training data that this one model doesn't get confused. And, 3 runs is a bit arbitrary.
True. And Model A2 just adds a confidence check.
Basically, A2 is Model A, but it adds a rule. The average confidence score for the majority result has to be 90% or more.
So not just stable, but confidently stable.
Right. It helps a bit with precision, maybe filters out some low confidence stable results, but it still has that fundamental weakness, just one model's perspective.
Okay. Model A, simple start, but yeah, pretty limited.
Yeah.
How did the sources suggest improving that detection power?
Well, the next logical step is Model B. It takes a different tack. Instead of repeating one model, you use multiple different models, but just run each one once.
Different models, like different types.
Yeah, exactly. The source mentions using EfficientNet, again our CNN.
The local detail guy.
Right. Then a vision transformer, or VIT, that's a different architecture, using attention to look more globally at the whole image.
Okay.
And maybe a SWIN transformer, which is kind of a mix, hierarchical attention. So different fundamental ways of seeing.
So you're hitting the input with different kinds of AI brains, basically. And the rule this time?
Disagreement. If 2 or more of these different models give different answers for the same input,
Flag it.
flag it as a data mismatch.
Yeah. Why does using different types of models help more?
Because they have different strengths, different weaknesses, different ways of processing information. A CNN focuses locally, a VIT globally. SWIN is sort of in between.
Right.
So if you feed them something unusual, like our molten gray fox, their different worldviews might lead them to different conclusions.
And that disagreement itself is the signal.
That's the idea. The conflict between them suggests something might be off with the input data, something that triggers their differences.
Okay, that makes intuitive sense.
Okay.
Like getting multiple expert opinions, pros, better O detection than A because of the diversity.
Definitely improves on Model A there. And computationally, it's often better than running one model multiple times, just one pass per model type.
But the cons, there must be some.
Oh, yeah. A key one is, how do you know why they disagreed? Is it because the data is truly weird? Or is it just because a CNN and a transformer fundamentally process images differently, even on normal data? It can be hard to tease apart.
So the disagreement might not always signal bad data.
Right. And that 2 or more disagree rule is pretty strict. It might flag perfectly fine data if the models just happen to have slightly different decision boundaries. False positives could increase.
And you lose the stability check from Model A, right? Since you only run each one once.
Exactly. You don't know if any individual model was internally stable or unstable on that input.
Okay. So Model B brings in diversity, which is good, but adds ambiguity and loses the stability signal.
Right.
Sources rate it intermediate for detection.
Right. And Model B2 just adds that 90% confidence check on the majority result again. Helps precision, but still has the single pass limitation.
This feels like we're building blocks. Model A checks stability, Model B checks diversity.
Which raises the obvious question, right? Can we have both? Can we combine the stability check and the diversity?
And I'm guessing that's where Model C comes in.
That's exactly what Model C does. That
Yeah.
You use the multiple different models, EfficientNet, VIT, SWIN, like in B. But now you run each of them multiple times, like in A.
Okay. How many times each?
Source again says 3 times each.
Wow. Okay, so EfficientNet runs 3 times, VIT 3 times, Swin 3 times, that's 9 runs total.
Yep, 9 predictions per input.
So what's the logic flow then? How do you decide mismatch?
It's a two-step process. First, for each model type, you find its majority prediction from its 3 runs.
Okay, so find efficient net's most common answer, VIT's most common answer, Swin's most common answer.
Right. You're getting the stable opinion from each model type first. Then you compare those majority results across the different model types.
Ah, okay.
If 2 or more of those majority results don't agree with each other, that's when you flag it as a potential data mismatch.
I see. So you check for stability within each model first, using the majority vote from its runs.
To filter out maybe just random noise from one run.
And then you check for disagreement across the model's stable opinions.
Precisely. It's designed to catch both internal instability. If a model can't even agree with itself over 3 runs, its majority might be weak or unclear, although the rule focuses on cross-model disagreement,
Yeah.
and the disagreement between fundamentally different architectures. Best of both worlds, in theory.
That sounds way more robust.
Yeah.
It must have the best detection ability of these 3.
It does. The sources rate Model C as having high detection ability. It accounts for both signal stability and diversity. Using that majority vote per model first also helps reduce noise compared to just looking at single runs like in B.
9 predictions per input. That sounds expensive.
That's the main drawback. High computational cost is the big one.
Yeah.
And it's more complex to set up and run, obviously. And even with this, the majority disagreement rule isn't perfect. You can still get some false positives or negatives.
And Model C2 just adds the confidence check again.
Yep. Model C2 is C, plus that 90% confidence check on the final majority result across the different models' majority votes.
And the sources rate C2 is the most precise overall.
Very high detection ability, according to the table. It's seen as the most precise among that whole set A, B, C, and their A2, B2, C2 versions for spotting data mismatch. But yeah, highest cost and complexity, too.
So looking back at that summary table in the sources, it really paints that picture clearly. Detection power goes up. A, low, Manda B, intermediate, Mandy C, high. And adding confidence helps, with C2 at very high.
But cost and complexity climb right alongside. A is low, B intermediate, C high, C2 very high.
Right, so AA2 maybe for quick tests, BB2 if you need better OD detection without breaking the bank, and CC2 when accuracy is paramount, especially C2 for high-risk stuff, but you pay for it.
Exactly. It's a
Huh.
trade-off. Which leads to, well, another question. If you really need the absolute highest precision, say, for medical images or autonomous control, is there a way to refine C2 even more?
How could you refine it more?
Well, think about Model C. We're comparing a CNN, a VIT, a SWIN. What if their disagreement isn't just because the data is owed, but partly because they're just fundamentally different beasts?
The basic architectures cause some disagreements regardless.
Potentially, yeah. How do we isolate the effect of the data being weird from the effect of the models being different types?
Okay, so how would you address that?
And this is where the sources introduce a really interesting evolution. Model C2. It takes the core ideas of C2, but tackles that model difference issue head on.
Ow.
It gets really clever. Instead of using different model architectures, Model C2 uses the same architecture for all its components.
The same, like all CNNs.
Yeah, the source uses EfficientNet, our CNN friend, as the example. But here's the twist. They're trained on categories structured at different levels of granularity. Detail.
Granularity, like zooming in, or like a hierarchy.
Exactly like a hierarchy.
Right.
Think of a family tree for categories.
Okay.
You might have a grandparent level AI trained on really broad stuff, like just animal or vehicle.
Got it. Broad strokes.
Then a parent level AI. Same architecture, but trained on slightly more specific categories within those. Maybe mammal or car.
Okay, narrowing it down.
And finally, a child level AI. Most detailed categories, like cat within mammal within animal, or sedan within car within vehicle, all using EfficientNet, just trained differently based on the category level.
Okay, same brain type, different levels of education. How does the prediction process work with these layers?
It's hierarchical, top down. You start with the grandparent AI.
Broadest level first.
Right. You run the input through that model 3 times, check for a majority prediction, 2 out of 3 agreement, just like before.
Yeah.
Then, and this is really important, you apply a confidence filter. But it's not just a single 90% threshold, it uses structured zones. We'll get to those.
Okay, zones, not just pass-fail.
Exactly. Now, if the input doesn't pass the majority vote check or it falls into a low confidence zone at this grandparent level,
Like, it's not even confidently an animal.
right, if it fails there, the whole process stops. It's flagged as a data mismatch immediately.
Fails early if it's totally out there. Smart.
Very efficient for filtering obvious weirdness. If it passes the grandparent level check,
You go down a level.
you go to the parent level. Run that model. Same architecture, different training, 3 times. Do the majority check. Apply the confidence zones for that level. Pass again. Go to the child level.
And so on, until you get the most specific answer, or it fails somewhere along the way.
Exactly. It has to pass the checks at each level to proceed downwards.
Why is this layered approach considered so powerful?
2 main reasons, I think. First, using the same architecture, like efficient net all the way down, helps isolate the issue. If there's instability or low confidence, it's more likely due to the data interacting weirdly with that specific architecture rather than just, a CNN disagreeing with a transformer because they're different.
Reduces a variable, basically.
Right. Second, that top-down filtering is super effective. It catches the really OD stuff, the black swans, early at the broad category level.
Before they can confuse the more specialized models lower down.
Exactly. If something isn't even confidently an animal, you filter it out before you waste time trying to decide if it's a specific breed of dog. It clearly isn't. This really helps precision at the lower, more detailed levels.
Okay, that makes a lot of sense.
Yeah.
Now tell me about these confidence zones. You said it's not just one threshold. The source called it the second filter.
Yes, the second filter. This is a really neat way to handle the uncertainty and bring humans into the loop effectively. So after you get the majority result and its confidence score at any given level, you see which zone it falls into. There are 4.
Okay.
Bright zone. Confidence is 90% or higher. This is your high confidence zone, considered definite recognition or validation. You proceed down the hierarchy, or if you're at the bottom, that's your final answer. All good.
Bright is green light. Go.
Exactly. Then you have 2 gray zones. First, gray zone 1, confidence between 80% and 89%. Moderate confidence. This is called conditional recognition, and it requires user review.
User review, like a regular person.
Potentially, yeah. Someone who needs to use the result might give it a quick sanity check. Flagged for review.
Okay. And the second, gray zone.
Gray zone 2, confidence between 70% and 79%. Lower confidence, also conditional recognition, but this one requires expert review.
Ah, so this needs someone with more specific knowledge.
Right. More ambiguous cases, maybe needing a specialist eye, also flagged, but for a different level of review.
And the last zone.
Dark zone, confidence below 70%. This is low confidence. Considered no recognition or invalidation. The data is treated as a mismatch at this level, and the whole process stops.
Okay, so bright is automatic pass, dark is automatic fail, mismatch, and the 2 gray zones are maybe, but needs human eyes with different levels of expertise needed.
You got it. It's a structured way to handle uncertainty.
That seems incredibly valuable, especially for high-stakes things where you need that human oversight for the borderline cases.
Absolutely. This whole C2 approach aims for maximum precision, very high detection ability again. It filters noise hierarchically and integrates human review in a smart, tiered way, really suited for applications where errors are costly.
Downsides. Got to be downsides.
Oh yeah, predictably. Very high computational costs. You're still doing 3 runs per level, potentially multiple levels.
Plus all his own logic.
Right. And it's complex to implement and manage, especially setting up the workflows for those gray zone reviews. That adds operational overhead.
And thresholds themselves, 90, 80, 70%.
A bit arbitrary, right? They'd likely need careful tuning based on your specific data, your models, and how much risk you're willing to accept in each zone.
Makes sense. You'd have to calibrate it.
Definitely.
Okay, so we've traced the strategies from simple A to the very sophisticated C2. Now, the sources mentioned you actually tested C2 on a big data set. Let's get into those results.
Right. So the tests used a pretty substantial data set. 650 categories. Started with more, but after cleaning and refinement, it was around 300,000 samples.
300,000 samples, 650 categories. That's pretty diverse.
Much more realistic than standard benchmarks, yeah.
Yeah.
It reflects real-world complexity better, and the goal was ambitious. Hit at least 90% recognition accuracy.
While using C2 effectively.
Oh, while using C2's whole hierarchical zoned filtering mechanism to weed out the mismatch samples before the final prediction.
And the result? Did it hit the mark?
It did. The test achieved 90% recognition accuracy on that refined data set using the C2 process.
Okay, so what does that tell us? Especially thinking through that Grok 3 perspective mentioned in the sources, the agreement-disagreement points.
Well, Grok 3's take, leaning towards agreement, is that this is pretty significant validation.
All right.
Because achieving that high accuracy, over 90% on such a large, diverse, realistic data set, shows that the CETO-FEES approach actually works in practice.
Hmm.
The hierarchical filtering, the zones, they do effectively catch and filter out the mismatch, black swan stuff, before it leads to a wrong answer being confidently accepted.
So it proves the concept works on messy, real-world-like data.
Pretty much. It shows that this structured approach delivers that high precision for ode detection that we talked about. It's not just theoretical.
Okay, that's the agreement side. What about potential caveats? The disagreement perspective Grok 3 might bring up.
Well, even 300,000 samples across 650 categories, it's big, but it's not everything, right?
The real world is always weirder.
Always. So that small percentage of errors, the less than 10% that didn't make it into the bright zone, might include those truly unpredictable black swan cases that just weren't represented, even in that large data set. Perfect detection is still impossible.
Fair enough. What else?
Grok 3 would also likely point to that 90% confidence threshold for the bright zone. It's quite strict.
Meaning,
Some samples that are maybe just slightly unusual but still technically correct or recognizable might fall below 90% confidence.
then get pushed to a gray zone, or even dark.
Exactly. So you might get false positives in terms of mismatch detection flagging valid data just because it wasn't perfectly prototypical and fell slightly below that high bar.
So the strictness helps catch real mismatches, but might overflag borderline cases.
It's a trade-off. Grok 3 apparently suggests that maybe relaxing that bright zone threshold a little, perhaps to 85%, could be beneficial depending on the application. You'd maybe accept slightly lower confidence for automatic validation to reduce the human review load or avoid flagging valid edge cases.
If false positives are a bigger problem than missing a few mismatches.
Right. And it reinforces the point that all those thresholds, 90, 80, 70, aren't magic numbers. They need tuning based on the specific context, the data, the risks involved.
Got it. But overall, the test sounds like strong evidence for C2's work on challenging data.
Yes, definitely weighted towards agreement. It's solid validation, and it really highlights the critical role of those gray zones.
The human review part.
Yeah, they're essential for managing that inherent uncertainty that remains. They provide that crucial bridge to human expertise, which is vital for trust, especially in high-stakes areas.
Okay, let's just quickly circle back. How might Grok 3's own features, mentioned in the sources, help with implementing something like C2?
Well, they seem quite relevant. Deep search mode, for instance, pulling info from the web, X posts.
How would that help?
Imagine a sample lands in Gray Zone 2, needing expert review. That expert could potentially use deep search to find external context, real-world information about that tricky input to help them make the right call.
Using outside data to resolve the AI's internal uncertainty.
Exactly. And think mode. Maybe that could help analyze why a model was uncertain, dig into the internal states to understand what tripped it up. Could be useful for troubleshooting or refining the thresholds.
And the API.
Essential. C2 is complex.
Huh.
Multiple model calls, branching logic, confidence checks. You need an API like the XAI API to actually build that workflow and integrate it into a larger system.
Right, you wouldn't build that inside the model.
No way. And finally, given the sheer compute needed for C, or especially C-Tune, remember those 9 predictions per input, potentially across multiple levels.
You need serious horsepower.
Yeah. So the SuperGrok subscription, providing those compute resources, becomes necessary to actually run these demanding strategies at scale.
Makes sense. You need the infrastructure.
Correct.
Okay, so let's try to wrap this up. We started this deep dive looking at AI's basic limits, generalization mismatch, pattern mismatch, being error blind, solution deaf.
The fundamental challenges.
Right. Then we walked through the strategies to detect data mismatches. Model A, simple stability check, but limited.
Model B, using diverse models, better detection but ambiguous signals.
Model C, combining stability and diversity, much better, but costly.
And finally, the highly refined Model C2. Same architecture hierarchically, using confidence zones for fine-grained uncertainty management and human review.
And your test results give strong validation that C2, this advanced approach, really does work effectively on realistic, messy data to hit high precision in filtering out ode and black swan samples.
Yeah, the evidence suggests it's a powerful technique, although complex. The key takeaway, I think, is that detecting when AI might be wrong is hard work. Achieving high reliability isn't free. It demands sophisticated strategies and significant computational resources.
That trade-off between accuracy, cost, and complexity is central.
Absolutely. But strategies like C2 show there are validated paths forward.
Which leaves us with maybe a final thought to chew on for you, the listener. Even with C2, the most advanced method we discussed, the AI isn't really aware it might be wrong. It's all based on statistical signals, patterns, confidence scores.
And C2 explicitly builds in human oversight for those uncertain gray zones.
So does this kind of tight, structured human-AI collaboration, especially managing that ambiguity in the gray zones, represent the most practical, trustworthy way forward for critical AI applications? Is this human-in-the-loop model the peak for now?
Or does the enduring challenge of the true black swan, that completely novel event that might slip through even C2's nets, tell us we need fundamentally different approaches to AI itself? Approaches that build in some genuine self-awareness or uncertainty representation.
Something to think about. Keep exploring.